Let's review redox reactions, and let's see if we can do that pretty quickly, because nobody has time to sit around and watch 7 hours of review on redox. So we're going to do this in like 3 minutes. Redox reactions are those reactions where electrons are transferred from one element to another. A wonderful example is the oxidation of zinc. Here we have zinc metal that is losing electrons to become positively charged. So this process is losing 2 electrons. But these electrons are transferred to another metal here, copper, which is in solution as ions. It's where the blue color is coming from, the copper ions. And as they are reduced to copper metal, metal is deposited on this zinc-plated piece of metal. And the color fades, which indicates that the copper ions are reduced. So here the electrons are transferred from zinc metal to copper ions, and the copper ions are deposited as copper metal here, and zinc turns ionic and aqueous in this case. All right, so how do I know what the charges are? There are some rules here. We're going to go through them all. And if you remember really well the naming and ionic and covalent bonding, you are halfway done with redox chemistry. Because if you understand that an element on the periodic table, such as beryllium or molybdenum or chlorine, when it's by itself, has still all of its electrons, valence electrons, intact, then you know it doesn't have a charge. So beryllium by itself, and it would get the phase label solid, would have a charge of 0, which is equivalent to the oxidation state. Now, in this case, they are the same, a charge and an oxidation state or oxidation number, but in some cases, in covalent compounds, there are no real charges, so we call that a hypothetical charge, and we give it a different name, so we call it an oxidation number. So in the case of chlorine, what happens, chlorine as its element is actually, when it exists as an element, when it hasn't received the electron to become chloride, which we know chlorine is eventually going to become chloride, but then it is reduced, okay, it gained an electron. But when it is by itself, it's diatomic. And so all of the diatomic elements, when they are listed like this, and that would be N2, O2, F2, Cl2, Br2, I2, and H2, okay? Those are all considered elements by themselves, and they all have an oxidation number of 0, okay? So that's rule number 1. Monoatomic ions, and I already put one up here, the chloride, they have charges, and their oxidation number is equivalent to their charges, right? So if we have iron 2+ or chromium 6+, the oxidation number is equal to the charge. But most of the time we do not have these ions by themselves. They're bound to another element in an ionic or covalent fashion. So then we have to follow certain rules. So these are the 2 big ones, oxygen and hydrogen. Now oxygen, just as a reminder, once again, if oxygen is paired up with itself, it has an oxidation state of 0, and the same is true for hydrogen. So this would probably also have a phase label. And so here they are 0. But when they are bound to either in an ionic compound or a covalent compound, right, like sodium oxide or carbon dioxide, then oxygen is always -2. Of course, we have exceptions. So here the element oxygen, each individual oxygen has a -2 charge. There's an exception, which is hydrogen peroxide. Well, there are other peroxides, but here oxygen is actually -1, and it's rare. And so 99 out of 100 times you're gonna have oxygen as a -2 charge. Okay, that's good to know. That's going to come in handy. In the case of hydrogen peroxide, you can actually look at rule 4, because rule 4 says that hydrogen is always +1, other than when it's here, and then we have some other exceptions when they're bound to a metal, but oxygen is not a metal. So if hydrogen here is +1, then oxygen has to be -1. And we'll come back to how I figured that out in a second. But so H2O +1, HCl +1, whatever it is, C2, H4 +1. See here, it's not a charge, right? So here we can argue +1 is a charge, because when you put this into water, you get H+ and chloride ions. And water is polar covalent, so that there's no real charge. But so this is a hypothetical charge. It's just an oxidation number, right? Okay. And then the exceptions are when they are with metals. Again, 99 out of 100 times hydrogen is going to be +1. There are some compounds like calcium hydride or sodium hydride where, you know, the metal is always positively charged. So in this case, and the name IDE hydride indicates a negative charge anyway, but those are exceptions. Moving on to rule 5, almost over, just 2 more. If we consider ionic compounds, we already know that the halogens gain 1 electron, and they all are negatively charged. They have a -1 charge when they are ionic and by themselves, so monatomic ions. But there are some exceptions. Only fluorine is the element that is always -1 when bound to anything else, whether it's ionic or covalent. Of course, always remember that F2 is the element by itself, so that would be a 0 oxidation number. Now, when chlorine or bromine or iodine, the other halides, are bound to oxygen or other halides, they can have different oxidation numbers. So, for example, we have the polyatomic ions we learned, the hypochlorite or the perchlorate. And so in those, chlorine here is bound to oxygen, so we don't know what its oxidation number is, and we will have to determine it. Now I'll come back to that in a second. Before we can answer that and determine what it is, we have to look at rule 6, which states that the sum of all of the individual atoms has to add up to the overall charge of a neutral compound, which is 0, or a polyatomic ion, which is -1. So in the above example here, the hypochlorite, the charge of chlorine plus the charge of oxygen has to be equal to -1. And if the overall charge is -1 and oxygen is -2, then chlorine has to be +1, because +1 minus 2 equals -1. So this is rule 6, which is probably the most important one. We can look at 2 atoms, and we can, most of the time, or all of the time, we can tell what one is and then determine the other based on that. So here we would do this calculation. 3 times x, sorry, it's just x because we have 1 chlorine, plus 4 times -2 equals -1, and when you solve for x, you end up with a +7 charge. See, we do know from one of the rules that oxygen is -2, and 4 times -2 is -8, and if chlorine is +7, then we end up with the overall charge. Now for the neutral compounds, we already know from naming on covalent compounds, when we name this compound here, we know that chloride is -1. And since there are 2, this is called copper 2 chloride, indicating that the charge of copper is +2. And therefore, in this redox chemistry scheme, copper has to have a +2 charge. Now, in this case here, this is a polar covalent compound, and it doesn't have charges, but it has oxidation numbers. And so we use the rules that we know already, and this rule 6, which says that the charge of carbon plus the charge of hydrogen plus the charge of oxygen, all of the oxygens and all of the hydrogens and all of the carbons has to add up to 0. Okay? So now we can use look at an example that could be reflective of what you might expect to see on an exam. So I might give you a redox reaction and ask you to determine the oxidation state for each element of the reaction below, or any kind of reaction. So you go through and you assign oxidation numbers according to the rules we've just learned. So you single out what we know, and we do know that oxygen is always -2. We got one here, -2. That's not a peroxide. This is not a peroxide, not carbon peroxide, although we'd love to call it that, but it's carbon monoxide, so it's not an exception. And we haven't gotten to 100 yet, because remember I said 99 out of 100 times. And then the other one we also know is iron here, so that's 0 because it's by itself. So we just determined a whole bunch of this below here, -2, -2, -2, and 0. Okay, so oxygen doesn't change, so that we know already cannot be oxidized or reduced, which is the follow-up question here. I want to know where's the oxidation, where's the reduction, which element is. So iron or carbon. So you can right now take an educated guess. Either iron is oxidized or reduced, or carbon. Let's see if we can actually figure it out. So now we can determine the charge or oxidation state of iron based on the 1-to-1 ratio. So this has to be +2. So we know that iron went from +2 to 0. It gained electrons, right? So that means it was reduced, or another way to look at it is the charge or the number was reduced from +2 to a lower number. So that's a reduction. So I can now answer iron is reduced. I can also answer that carbon is oxidized, because it's the only, I can't speak in blah, oxidized. Okay, let's try that again. Oxidized. That's much better, because it's the only element left, so it must be the one gaining the electrons. But I still need to fill up this table here, and so carbon in carbon monoxide has to be +2, and carbon in carbon dioxide has to be +4. Again, we have to take the charge of carbon, which I'm going to make X, plus 2 times the charge of oxygen, which is -2, has to be equal to 0. So if I solve this for X, I get that this is +4. So this is +4, and so I know that there are 2 electrons that are lost. +2 to +4 means 2 electrons are lost. But I don't even ask you this in this problem here. You have just gotten all of the credits. Okay, so this is it in a nutshell. Good luck, and I'll see you at the next tutorial.